2020 Perseverance mission, which is currently midway through a 7-month cruise to Mars that will land a car-sized rover on the red planet in February of 2021. Before working for NASA, he earned degrees from Harvard, Cambridge, and MIT, and now he lives in Pasadena with his family. I hope everyone really enjoys this presentation. We'll have plenty of time for questions at the end, so feel free to type any questions you have in the Q&A box on the side of the screen. It should be on the actual Zoom box that you're actually looking into right now. And this video is also being recorded, so if you have any questions or if you have to drop out for some reason, you can always catch up later and watch the video in full. Now I'll hand it over to Matt, and just want to say thanks so much for being a part of this.
Awesome. Thanks so much, John. And just great to be here. I'm really grateful for this chance to talk to the poly community. Thanks also to Catherine Vieser and Aaliyah Daniels for coordinating all this. So as John mentioned, I graduated in 2003, and I definitely felt the pull of JPL during my years at Poly, all the way from middle school and down to lower school. So Charles Alachi, who was a senior scientist at JPL when I was in lower school, was a big figure and would come and give us talks at Poly, and we had some field trips to JPL. So it sort of always loomed large in the distance, and managed to find my way back here. I also wanted to mention someone else at the sort of center of the Poly JPL nexus for me, which is Eric Antonsen. He was a professor at Caltech and the chief technologist at JPL, and has been a mentor to me. So want to give a shout out to those individuals. So I came to JPL in 2014. Before that, I earned a PhD, and I actually was an intern at JPL for several summers in college, just staying at home and riding my bike up to lab. So it's great to be here as a full-time employee. But enough about me. I want to talk about this really interesting mission we have going on, the Mars 2020 Perseverance rover. It's in flight right now. I want to talk to you all about the design of the mission, how we get to Mars, how we land on Mars, and some of the awesome new technologies we're demonstrating with this rover. So feel free to ask questions in the chat, and we'll definitely get to them afterwards. So I'm going to go ahead and share my screen. There we go. All right, so this is one of my favorite pictures, and this is actually the Mars Curiosity rover, which is sort of like the older sister of the Mars Perseverance rover. Perseverance is kind of a copy of Curiosity. It uses the same general chassis, although Perseverance, the one we launched in July, and it's on the way to Mars now, has some new instruments that'll do some really cool science that I'll talk about in a second. But one of the reasons I love this picture so much is that it really gives you like a sense of what it would be like standing on the surface of Mars. The rover has a robotic arm, and that arm has a little camera on it, and it actually uses that camera to point back at the rover and stitch together a bunch of small photos to get this nice big panorama. So it's sort of like a interstellar selfie or something. But the rover itself is sitting in what's called Gale Crater, and you can see the rim of the crater way off in the distance. Up on the left is Mount Sharp, which is the big mountain that Curiosity landed right next to, and it's actually on its way up the mountain slope because there's a bunch of layers of rock there that provide an interesting glimpse of the past geology of Mars. So it's a beautiful like desert landscape you see here. There's some dust on the rover. It's also a very harsh and unforgiving landscape, and that's a big part of what goes into engineering the rover. So Mars is really, really cold. So on average, it's about -64 degrees Fahrenheit. It can drop down as low as -200 Fahrenheit almost at night. Mars has a very thin atmosphere. It's about 1% of the atmosphere of Earth. It's mostly carbon dioxide. So you couldn't really breathe if you were standing there. And also Mars is really, really far away, which causes some interesting challenges operationally that I'll talk about. This is a picture that Curiosity took of Earth looking back. And when Curiosity took this photo, Earth and Mars were about 100 million miles away. So Earth was just a tiny star in the night sky, just the way that Mars for us is a tiny star in the night sky. And the distance between Mars and Earth can vary from around 35 million miles to 250 million miles. So it's, really, really long distances we're talking about. It makes communication difficult. We'll talk about that in a bit. It also means that Perseverance rover, once we land it, just like the Curiosity rover, it's on its own. You can't call AAA on the surface of Mars, so you really have to bring all the things with you that you think you're going to need. And so we'll talk about that too. Finally, Mars is pretty far away from the sun. It's the next planet out. That has implications on how we get power to the rover, and it plays a role in the temperature as well. So I want to back up a little bit and talk about what this mission is trying to do. It's been in development for almost a decade now, and it's really about understanding the possibilities of life on Mars. And when we talk about life on Mars, we're not talking about little green men right now, and we're not even talking about like dinosaurs or large-scale fossils from the past. We're really talking about ancient microbial life. So small single-celled organisms that possibly existed back in the time when Mars was a lot warmer and was a lot wetter. And so that breaks down into a few goals. One is we're trying to understand the geology on the surface of Mars. And you'll see in a second what I'm talking about with where we're going to be putting this rover specifically. But if we can understand the geology, there are certain minerals that form only in the presence of liquid water. So NASA has this philosophy of following the water, because everywhere we see liquid water on Earth, we see life. And if we're going to try to find life elsewhere in the solar system, trying to identify places with liquid water is a really high priority. So some of the other Mars missions have found evidence of past liquid water, and we're looking for evidence of liquid water at the past liquid water at the site we're going to land on in February. The second objective is astrobiology. So using sophisticated instruments to look to see if we can find the chemical markers of biological processes that were on Mars, in billions of years ago at this point. So byproducts of ancient life, not necessarily fossils themselves, but things that we think could only be the result of some sort of ancient microbial life being existent at that time. And then finally, we're also going to be what we're calling caching samples. So we have a robotic arm, which I'll show you, and we have a coring drill. We can take about 40 rock core samples and store them in the rover. And this is actually like the first leg of a round trip to Mars. NASA is planning later in the 2020s to send a robotic fetch rover to grab those samples from the Perseverance rover, put them on a small launch vehicle on the surface of Mars, launch them back into Martian orbit, and eventually get them back to Earth. And the thinking there is that we can only send a few small instruments to the surface of Mars. If we get samples from Mars back to Earth, we have a whole huge laboratories that are much more sophisticated than anything we could ever send to Mars. We have those laboratories here on Earth, so if we can bring the samples to Earth, we can do a lot more sophisticated analysis and really dig into the science questions that we're trying to answer with this mission. One other thing the mission's trying to do is prepare for potential human exploration of Mars. So there's an experiment on board called MOXIE, and what it does is it sucks in carbon dioxide, which is most of the atmosphere of Mars, and it creates oxygen, and you can use that for breathing. If you have human exploration there, you could also use it for rocket fuel. So we think that if we were ever going to send a human mission to Mars, we would need to manufacture our own oxygen on the surface. And this MOXIE instrument is a technology demonstration to try to kind of see how that would work in practice. All right, so this is where Perseverance is going to be going. This is the Jezero crater, and it's the landing site for Perseverance. It's about 45 kilometers wide, and the landing ellipse is shown there in black. And you can see it's kind of like a typical crater, has a ridge around the edge, surrounding a depression. But if we zoom in on the landing site, you actually see a very interesting feature here, which is what we think is an ancient riverbed that sort of snakes here on the top left and then empties out kind of in the middle of the frame here, and then fans out like you'd see a river delta here on Earth. So we believe that this was a location where we have visual evidence of flowing water in the past, and that makes it a prime site to go and actually look for these signs of ancient microbial life on the surface of Mars. It's a hard problem though. This is a pretty treacherous place to land. There are a lot of, it's scientifically interesting, but there's a lot of features on the ground that make it difficult to put a car-sized rover down safely. So Perseverance has some new landing technologies. I'll talk about them a little bit later, but it's called terrain relative navigation, and it's sort of like a visual approach to landing and trying to autonomously look for hazards and avoid them during the landing process. So a really cool scientific site, but a pretty hard place to land. So there'll be a lot of I guess people holding their breath on February 18th when we land on Mars. This is a picture of the rover, kind of a cartoon view with some of the big features labeled. Like all the other rovers we've sent to Mars, you can see it has that 6-wheel, we call it a rocker bogie suspension system. It allows the rover to climb over rocks that are up to the size of the wheels themselves. And up on top here, we have what's called the remote sensing mast, or RSM. There's a ton of acronyms in aerospace, I'm sorry to say. So John, you'll have to keep me honest if I get into alphabet soup here. But that mast is sort of like, the Wall-E head of the rover. It has a bunch of cameras on it. It has some instruments. And then out here is the rover's robotic arm, which it uses to place additional instruments and the drill up against rocks in order to do like detailed investigations of those pieces. There's a bunch of other components here on the rover, some of which we'll get into. We can talk about it in the Q&A. There are some antennas, like this little cam back here is an antenna. There's one on the other side. This sort of thing that sticks out the back is called the radioisotope thermoelectric generator. It's basically a decaying piece of radioactive material that is like a thermal battery. It keeps the rover warm, and it also charges the batteries in the rover. And what this slide is calling out is all the different instruments on board. So I talked about MOXIE already. That's the thing that's going to be producing oxygen from the Martian atmosphere. We also have something called RIMFAX, which is a subsurface radar. It can penetrate the first few meters of the Martian soil to determine what the geological composition is in the vicinity of the rover. Up here on the remote sensing mast, there is this big thing here called SuperCam. It's actually a infrared laser that can zap rocks from a distance, and then it looks at the vapor that is produced by that zapping, and it can detect the chemical composition of the rocks from a distance. So that's kind of cool. We also have these panoramic cameras that will be generating these really amazing, high detailed panoramic views of where we land and where we rove. There's a weather station on board called META. It can detect like the wind speed. It actually has a microphone, so it can listen to what the wind sounds like on Mars. It has some cameras that look up to measure the cloud cover on Mars. So we really are trying to develop this holistic view of what it's like on the surface of Mars when we send this rover. And then on the end of the arm here, we have two what are called spectrometers. What these instruments do is they bombard rocks with radiation, either ultraviolet radiation or X-rays, and then they measure the basically the fluorescence that comes back from those rocks, and that kind of gives a fingerprint of the elements that are within the rocks, and that is part of what helps us determine if we can see signatures of ancient microbial life with those spectrometers. Finally, at the end of the robotic arm, we also have a really capable drill. It can take rock samples and it can transfer them back into the rover for that sample caching objective that I talked about earlier. So a lot going on the rover. We're going to talk mostly about actually how we built it and got it to Mars and landed on Mars, and less about the surface mission, but we can always dive into the surface mission as part of like the Q&A. Happy to talk about it. I just happen to have worked more on the design and the cruise phase of the mission, like the getting to Mars part. So I guess a little biased. This is sort of a crude timeline of the mission. We talked about the landing site, Jezero Crater. It was selected back in November of 2018. That whole time, the rover was being built or designed and built, put together. And then we launched in July of 2020. And we're in the middle of our cruise to Mars. It's about 7 months long. We landed February. We have about 72 days left until landing. So just right in the middle of trying to get this thing to Mars in one piece, healthy, ready to land on February 18th. It'll land on Mars. There's this, you might be familiar with the 7 minutes of terror. That's the time it takes to get from the top of the Martian atmosphere down to the surface. It's a really complicated technical problem that we demonstrated on the Curiosity rover. We're going to try to repeat it with the Perseverance rover. And then surface operations. So surface operations will be 1 Martian year, which is about 2 Earth years. That's the planned mission, but for any of you who are familiar with any of the other Mars rovers we sent, they tend to last a lot longer. Curiosity landed in 2012, and it's still going strong. So hopefully Perseverance will last a long time too. So here's the finished rover. It's the fully assembled rover at JPL. This is in the clean room high bay, and actually at JPL they just put a big, like 30-foot tall NASA logo on the side of this building. So if you're driving up the 210, like from Pasadena towards La Cañada, and you look out to the right, on the other side of the watershed, you should see that big NASA logo, and inside that building is where this picture was taken. You can see the rover here. We're testing out the mobility subsystem. So you see the wheels up on this, this ramp here. The rover weighs about 1,000 kilograms. The mass is about 1,000 kilograms. So on Earth, it weighs about 2,000 pounds. So it's like, you know, a car-sized thing. Martian gravity is about 1/3 of that on Earth. So it doesn't weigh as much on Mars itself. But you can see the parts we talked about on that cartoon. You have the remote sensing mast up here. There's a red cover over the supercam aperture. There's a antenna back here, that garbage can looking thing that I pointed out previously. The robotic arm is up here on the front, and it's sort of tucked in. The robotic arm has 5 degrees of freedom. It has an elbow with 2 joints. It has, or excuse me, a shoulder with 2 joints. It has an elbow with 1 joint, and then a wrist with 2 joints. And it can kind of tuck the arm in under itself for driving. We assembled the rover in this clean room in order to keep everything pristine. When we have these big panels open and are looking on the inside, we don't want dust to come in and damage any of the really sensitive electronic components or any of the instruments. So there's a huge HEPA filtration system that's constantly turning over the air. You can also see everyone is in these bunny suits to protect against skin cells coming off. Also, these suits have special properties where they help protect the rover against basically accidentally zapping it. Like it's super dry right now in California, and I feel like I'm shocking everything in the house. And so we control the humidity and temperature, and we wear these special garments to prevent damage to the rover as we're assembling it. So this is actually looking inside the rover body. We call this shot the belly of the beast. And you can see all the cabling here, tons of electronics equipment. In aerospace, we call electronics like this the avionics. It's just electronics that fly. And so we have computers and radios. And notice I said computers plural, and that's intentional. They're the main brains of the rover, and actually we have 2 of them. And that's kind of the philosophy of we're going to Mars, this planet that's hundreds of millions of miles away. We can't really service it, so we got to bring 2 copies of almost everything. So we have 2 computers, 3 radios, multiple copies of the essential things that we need to operate on Mars. The radios themselves can communicate either directly to Earth using these large antenna dishes that JPL runs called the Deep Space Network. There's also a series of orbiters that are around Mars, like science orbiters that, for example, took that picture of Jezero Crater. They also have radios that can talk to the rovers, and we can send commands through those orbiters as like a relay. And actually, that's the way we get most of our data back from Mars, is not directly to Earth, but we send it from the surface of Mars up to one of the orbiters around Mars, and then it comes back to Earth from the orbiter. So I have let's see, we'll jump in here. I actually have a video that shows more of the mobility testing. So let's see how this looks to you guys. So this is the first drive of the rover once it was all put together and all the wheels were in place. So you can see it drives pretty slowly. This is like close to top speed for the rover. So it's nice and slow and steady. You can see a ton of people taking a really careful look at the rover. It has a 6-wheel drive, so each of the wheels has its own motor. And then the front 2 and back 2 wheels have steering actuators, so it can steer kind of like a car in like an arc. It can also turn in place, and you'll see that in a second. One of the things that Perseverance focused a lot on was the wheel design. So the wheels on Perseverance are actually different than the wheels, there's the turn in place. The wheels on Perseverance are different than the wheels on Curiosity. The Curiosity wheels got kind of beat up, and so we've learned a little bit about how to better design wheels to operate, for a long time on the surface of Mars. So that was a kind of crash course in the rover, and there's like a ton more we can talk about. But of course, we have to get the rover from Earth to Mars in one piece. And this is an expanded view of how we do that. The rover is right here. And what we do is we collapse the remote sensing mast on top, tuck in that robotic arm, fold up the wheels, and fit it in underneath this piece right here, which is called the descent stage. And I'll show a video later on that shows like how that descent stage works in action. But it's basically like a jetpack for the rover. There's a portion of the entry, descent, and landing sequence where we're actually flying the rover underneath that descent stage, guiding it to the right place on the surface of Mars. Pretty cool. And so that rover and descent stage unit is then packaged into the aeroshell and the heat shield, and that protects the spacecraft from, it protects the rover during entry into the Martian atmosphere. So we slam into the Martian atmosphere at a really high speed. There's a lot of friction that's generated when we do that, and this aeroshell and heat shield protect the rover as it's going through that harsh heat of the Martian atmosphere. The aeroshell also is what lets us almost fly the vehicle through the Martian atmosphere as we try to get to our target. It's a guided entry system, so we can actually fly. There's a difference between the center of mass and the center of pressure for this thing, so it actually can kind of fly and move itself to the right place. And I'll talk more about that in the future, but that's a big part of what this does. And then this little piece on top, this disc here is the cruise stage. That has thrusters, it has solar panels, it has some fuel for those thrusters, and some other electronics. And that's what turns this whole thing into a spacecraft, really. It powers us on the way to Mars, and it lets us do our trajectory correction maneuvers, which are kind of like our little course adjustments on the way to Mars. So it's really kind of like this cool Russian nesting doll that all fits together. And it's also kind of like I call it like a transformer. So we have, we go from a spacecraft, in space, to kind of like an airplane that flies itself through the atmosphere, to sort of like a hovercraft with the descent stage, and then finally to a rover on the surface of Mars. It's pretty incredible to watch and to be a part of. So this was the cartoon view. And then over here we have the real thing. So you can see here the rover, its wheels are sort of tucked up underneath, and you can see, I don't know how easy it is to see over the Zoom feed, but you have these rocket engines here from the descent stage, and then there's the aeroshell up here, and then down here is the heat shield that all gets sandwiched together nice and cozy, and there's the cruise stage up here. The thrusters are underneath this little red cover. There's another one on the other side you can't really see. And then here's a tank right there. And the solar panels are on the top. We can't see them in this view. So yeah, this picture was taken just before it was all put together. And the next time these pieces come apart will be at Mars. So that's pretty neat. So putting all this stuff together was a huge effort, and we do a ton of testing to make sure that it will work properly. Once we get to Mars, it's a harsh environment, and we need to make sure the components are all ready to do their job. So I have another video here that shows a little bit about how we do all that testing. So we're back here in the JPL clean room. There's the cruise stage. And here's some folks getting the two together. There's the descent stage we talked about, and then putting it all together. a lot of really big equipment we use to move the different large pieces around. Each of these pieces weighs a few thousand pounds. We take it from where we assembled the spacecraft up to another building at JPL where we have this thermal vacuum chamber. And this can simulate the hot and cold temperatures of space and also the vacuum of space. We then took it back into the clean room. Here you can see how we designed and built the wheels. Once we get it back into the clean room, we did a lot of tests of the robotic arm, check out everything, check out the cameras, the instruments. A lot of detailed work goes into building this thing. You can see everyone wearing their bunny suits to keep the hardware safe. I like that shot right there, showing the robotic arm moving through all of its different motions to get back into the stow position. And there you are. You have a tested rover ready to go. And that whole process takes years to test everything and get it just right. So once we built the whole thing and tested it at JPL, we took it apart again, not all the way, but partially, and loaded it into a bunch of containers and took it out to March Air Force Base in Riverside and loaded it onto a C-17 cargo plane. And that's what this picture is. This is Dave Gruhl. He's the manager of the spacecraft assembly process. And he is seeing off his baby here that he worked years and years to put together. I like that the shipping container itself has its own little air conditioner. We keep everything super well controlled. It flies over to Florida. That's where we launched from. And this is the spacecraft being packaged up inside what we call the launch fairing. That's just a fancy name for nose cone. Spacecraft goes into the two halves of the nose cone. On the right here, we have the bottom portion of the Atlas V rocket that we used to launch the rover. It's a huge rocket. It's 190 feet tall, weighs over 1 million pounds when it's fully fueled. But the spacecraft is just like one little teeny bit at the very top. And we need all of that fuel and all that energy to get the spacecraft on its way to Mars. So I have another video here to show of launch day. This was July 30th of this year. And it was a beautiful morning in Florida. It was about 7:50 a.m. Eastern time, so nice and early, 4:50 local. Most of the JPL team was actually at JPL. We had to be ready to assume control of the vehicle once it was in space, so everyone was at JPL watching. The acceleration here is pretty incredible. After only about 90 seconds in flight, the rocket's already going over 3,000 miles per hour. The spacecraft popped off of the launch vehicle. That's separation, critical milestone. This was the scene back at JPL during initial acquisition. This is when we detect the first signal from the spacecraft and establish two-way communication. It's a really important thing. We couldn't do the rest of the mission if we were not able to establish a radio link with the spacecraft. So a couple things. This was the control room on launch day. So there I am, dutifully monitoring telemetry from the spacecraft. You'll notice a couple things that might be different from other pictures of this room that you might have seen. First of all, we're here in our COVID time, so there aren't as many people in the room as you would otherwise see. We had people spread out throughout the building. You could fit almost double, maybe even more, the number of people in this room than we had, and you can see these empty chairs. Everyone's has a good 6 feet of distance. Everyone's wearing masks. The flight director stands up here at the front of the room, and there's this plexiglass partition here. Since he's facing the rest of us, there's this partition here to keep us all separated. They've also done other things like increase the air exchange in the building to try to bring in more fresh air from the outside, for example. On launch day was also interesting. Like I mentioned, it was about 4:50 a.m. Showed up around midnight to start the shift. And I don't know if you guys remember this, or at least the people in Southern California might remember that on July 30th we had a earthquake, and it was about 20 minutes before launch. So that definitely kept us on our toes, and we were making sure that all of our data connections were still good, that we still had power to the building. We're on a voice loop with the people in Florida, so we let them know that we had an earthquake, and it was a little bit an interesting time, but everyone was very calm, and we pressed forward. One of the big things was when we contact the spacecraft for the first time, that initial acquisition, and that's one of the big reasons that everyone is here at JPL is we're monitoring the signals from the spacecraft so that we can lock onto it and start really commanding it at the start of the mission. So once we're actually in flight, we have to do a few things to get to Mars the right way. So one thing you'll notice is that the trajectory to Mars it's shown here in this white line. Earth at launch is here, and Mars at launch is here, and we don't do just a straight line shot to the red planet. We actually take this curved trajectory that takes us 7 months to get there. So once we get to Mars, Mars is here, and Earth is all the way over here. And the reason we take that trajectory is we're actually the spacecraft in orbit around the sun, and we're more or less coasting on our way to Mars. We have to do a couple of things though. We don't target Mars directly. NASA has rules about planetary protection, they call it, where we can't just launch something uncontrolled to another planet out of fear that maybe some microbes that are on board the spacecraft or on board the rocket would maybe impact Mars and sort of contaminate this otherwise pristine piece of nature, which is this other planet. We do a lot of hard work to clean the rover, but the launch vehicle isn't necessarily that same level of cleanliness. So in order to prevent contamination from the launch vehicle to Mars, we bias away from the planet, and we have to do these trajectory correction maneuvers to bring ourselves back to actually target the right point. The early maneuvers we could do up to 6 of them. The early maneuvers are all about removing that bias that was in the rocket. And then the later ones are really about fine-tuning our approach. And you can see how they get closer and closer as we get closer to Mars. We've done TCM 1 and 2 already, trajectory correction maneuver 1 and 2. And TCM 3 is coming up in a couple weeks here. And hopefully we can just do one more, but we have opportunity to do 5 and 6 as well. But that will really put the spacecraft right at the right point to start our entry, descent, and landing sequence, which I'll show you in a sec. One kind of cool thing I want to highlight for folks is this website that NASA has. It's called NASA Eyes, and there's a link at the end of the presentation, but it lets you see in real time where the spacecraft is. So it relies on real data from the spacecraft to make this visualization. It shows some stats over here. So about 55 million miles from the Earth, going about 55,000 miles per hour relative to the sun. And you can grab it here and kind of pan around. So if we go over here, there's the sun back there. And then if I go over here, there's the Earth. And so that's looking back. And if I go over here, you can see Mars down there. So that's where we're headed. You can also click on this spacecraft location icon, and it'll zoom out to show where Mars 2020 is in relation to Earth and Mars. So you see this looks kind of familiar from the other picture I just showed of all the TCMs. But yeah, and you can see we're getting pretty close to Mars here. Still 72 days to go, but this we'll keep getting closer and closer, and folks can bring this up at home and keep an eye on where Mars 2020 is at any given time. Also, it shows all the other NASA missions and all the other planets in our solar system as well. So it's a pretty cool tool you can use to sort of visualize how everything is going out there in the solar system. So let's see, we'll come back here. When we come back, when we get to the end of cruise, the next step is what we call entry, descent, and landing. And it's a really intense time. It's the process of getting this spacecraft from space safely onto the surface of Mars. So we land at about 2 miles per hour on the surface of Mars. We come in at about 12,000 miles per hour. So we have to go from 12,000 miles per hour to 2 miles per hour, all by itself. By the time we get to Mars, Earth and Mars are so far away that it takes 11 minutes for a radio signal to get from Earth to Mars 2020 and from the spacecraft back to Earth. We call that the round trip light time. Or excuse me, the one-way light time is 11 minutes. The round trip light time is 22 minutes. So we can't like manually fly this thing down to the surface of Mars. We have to rely on it doing itself automatically. So it's a huge challenge. I have a video that we'll walk through. Let's see. So here we are. This is animation. And once we're at Mars, we don't need the cruise stage anymore. So one of the first things we do is we pop off that cruise stage. It separates about 10 minutes before we hit the top of the atmosphere. We're going about 12,000 miles per hour at this point. And so that heat shield generates a ton of friction as we hit the top of the Martian atmosphere, and it glows red hot. The rover inside is nice and comfortable, but the heat shield gets really, really hot. We also have some jets on the back shell that, like I mentioned, help kind of guide us through the Martian atmosphere. So we're actually flying to our intended, target point here. You can see those thrusters firing. Once we're inside the atmosphere, we're still going over 900 miles per hour. So we deploy a parachute, this supersonic parachute, the largest it's ever flown, to slow down the vehicle even more. The problem with the Martian atmosphere is that it's not thick enough to let us go all the way down on the parachute. There's not enough drag. So we have to detach from the parachute and use that descent stage to fly down on our jetpack. And this actually worked for Curiosity back in 2012. So there we go. This is what we call powered flight. And the rover is underneath the descent stage. There's a radar that locks onto the ground to know how far away the ground is. And there's sensors that allow the descent stage to know how it's moving, what the velocity is. We also have a set of cameras on board the descent stage called the landing vision system. And what it does is it takes images of the terrain and it compares those images with an onboard database of known images and, more importantly, known hazards. So it can look at the ground and steer itself away from hazards. And as we get close to the ground, the rover is reeled out on this 65-foot long tether, and the descent stage slowly lowers the rover down. We call this the sky crane maneuver. And this is the point at which we're slowly going down at about 2 miles per hour to actually put the rover directly onto the surface of Mars with its wheels. So descent stage has done its job. We cut the bridle, it goes off and crashes a safe distance away. And the rover is then left on the surface of Mars to do its service mission. So everything's all folded up, and we'll deploy the sensing mast, deploy some other things, and get ready to do the mission. So that's like the high level view of what we're going to be doing with this mission. We land on February 18th, 2021. So you can tune in. NASA will be broadcasting it. Should be a pretty exciting day, and we'll do all that stuff in real life instead of through an animation. So that's most of what I have. Happy to talk questions. I don't want to I want folks to have a chance to ask questions, have a discussion. Yeah.
Thank you so much. That was amazing. I really, really enjoyed that. We have a ton of questions, so I'll try and get to all of them. Please, you can just enter them in the chat or the Q&A, and I'll get through them. So if you're listening, please feel free to submit any questions that you have. So let's start with one of the earlier slides was about water on Mars. We had someone write in asking if you were familiar with if you could just talk about kind of the lakes on Mars. Are they hypothesized, and are there any efforts to dig into lakes of Mars more specifically?
Yeah, that was a good question. So I think that this person was talking about some technologies that are in development on Earth for exploring like waterways and lakes. Could those be applied to Mars? And Unfortunately, Mars doesn't have any liquid water currently. The atmosphere is so thin and it's so cold that water on the surface of Mars is ice, and when it's exposed to the atmosphere, it basically sublimates. It goes straight from solid to gas, the same way that dry ice does here on the Earth. There's some arguments about liquid water being like in existence in very, very specialized circumstances on the surface of Mars, and the water would have to be extremely salty, for example. But we don't really have, there aren't any water lakes on Mars the same way there are on Earth. That said, there are liquid lakes on other places in the solar system that are interesting places to explore, like the surface of Titan, which is the moon of Saturn, has liquid methane lakes, which are extremely cold. Liquid methane is, much, much, much colder than liquid ice, but it's a liquid. And there have been discussions of maybe sending, robotic ships to explore the liquid lakes of Titan.
That's awesome. We have someone says, please say hi to Adam Steltzner from UC Davis Engineering. I don't know if you know who that is.
Yeah, so he's they say that he's NASA Elvis, so he's our chief engineer. And if you look at the some cool YouTube videos out there, like if you just Google like 7 Minutes of Terror MSL, then you will definitely see him. He's a pretty charismatic guy, and he actually was responsible for coming up with that sky crane architecture. And it's one of those things where, like, as he says, it on the surface it sounds crazy, it looks crazy, and but it's actually the result of very well thought out engineering. But yeah, he's our chief engineer, and he's a very interesting guy, good guy to have on the team.
That's awesome. We got another question about MOXIE, and specifically, how do you convert carbon dioxide to oxygen? Could you talk a little bit?
Oh boy, yeah, this is definitely out of my wheelhouse. So the oxygen and carbon dioxide and carbon are obviously like chemically bonded. So I believe it has to do with a combination of heat and really high electric fields to strip off those bonds to be left with just the oxygen. But I don't want to go too much further than that, because unfortunately I don't know as much about MOXIE as
Yeah, I think the extent of my experience is like when you take some water, apply some electricity, and you get the oxygen and hydrogen separately. I don't know if you could do that with carbon dioxide. Probably a little bit trickier. So someone wanted to know what radio frequencies are used to communicate with Earth, and maybe you could just talk a little bit more about that.
Yeah, so we use what's called X-band to communicate directly to the vehicle from Earth. The frequencies are around like 8 gigahertz.
Is that high or low?
That's, I don't know. It's all a continuum. I guess it's high. So a lot of like it's a higher frequency than, say, like when we had over the air TV.
Sure.
But it's lower than say like what satellite TV comes down at, which is like a Ka band. It's like a higher frequency. It's also lower frequency than like 5G cell phones, I think.
Okay.
So that's what we use to talk directly to the spacecraft or to the rover when it's on Mars. But I talked about these orbiting relay orbiters at Mars. So these are spacecraft that are orbiting Mars right now, and they can talk to the surface of Mars using UHF, which is around like 400 to 500 megahertz. So a lot lower frequency. And because the orbiters are closer to Mars, they're only like several hundred kilometers from Mars versus like millions of kilometers, they can use this lower frequency to get pretty high data. And then the orbiters shove it back to Earth using X-band.
Got it.
Yeah.
1 second. Yeah, we have a question from someone who would like to speak.
Awesome.
Welcome to Alessandra. You should be able to speak now, but you're on mute. I think you need to unmute, and then you can ask your question. Let's see. We can do one other question while she's getting set up. Somebody wanted to know a little bit more about your path through just kind of the educational system. You know, obviously Caltech.
This is my question too.
Oh, great. Here, please ask away.
Oh, hi. I'm so impressed. Thank you for sharing your expertise. It's always fun to see behind the curtain of engineers because it sounds so abstruse. And here you are, a Poly alum, doing what you're doing. My name's Alessandra Bianchi. I'm class of '82. I'm admittedly a liberal arts English-French major, but married to a MIT engineer and have spawned an engineer. And so I'm making up for lost time. My question was, given your job description and duties today, were there skills you learned at Poly that you are applying daily, monthly, weekly, or are all the degrees you have, you know, necessary and useful in your day-to-day, or is it really specific and you get qualified by those degrees and then you learn what you really need to learn on the job at JPL?
So I'll start with the last part first. I think it's I think it's mostly the latter. The degrees help with qualification, and it's at JPL, the engineering staff is, I think, like about a third like bachelor's, master's, and PhD. And so I got a PhD because I was always interested in fundamental research, and that's been part of what I've done before this and hopefully after. But definitely don't need a PhD to be an engineer at JPL. And like you say, a lot of it is like on the job training, especially my current role as flight director. It's sort of like bringing the knowledge from building the spacecraft into like mission operations, but then also shadowing the more experienced flight directors and seeing how they react to different real-time situations to gain confidence and gain expertise in dealing with how we operate the spacecraft. So yes, definitely a lot of on-the-job learning. And during my internships at JPL, I always thought that that like I learned more in like a summer at JPL than like a whole semester in college.
Wow.
And the first and then so I forgot the first part of your question. So if you ask that again,
it was about Poly, the skills you learned at Poly, in case
Yep.
there are any that are coming in handy.
Yep.
Poly and others might want to know that.
Yeah, definitely. Yes. So the job I have now and being at JPL is definitely a huge team environment. So being a good team member is extremely important. You know, anything like this this complexity, you interact with a lot of people from different backgrounds. Being able to work cohesively is really, really important. And I feel like that's something I learned at Poly through my different activities I did. So I would encourage everyone who wants to work in this area to kind of be aware of like the team environment and your team skills. Another thing is writing. I think I learned how to write really well at Poly. And I think it's served me well, even though I work in a technical field. We have to communicate really, really challenging topics, and even amongst engineers, it can be hard to speak the same language. So good communication skills are really helpful, even in a technical job. And I credit Poly with that too.
Great.
Excellent. Well, thank you.
So can
I ask a tangential PS, because it's just
Sure.
kind of I went to summer camp riding on horseback, Tom Sawyer camp, in the sand pits behind JPL. Are the trails still there, and do people go on horseback behind there?
Yeah, actually a ton of mountain biking. That's like the big thing is
okay.
Yeah, but yeah, horses too.
Interesting. Well, thank you so much. Very impressive and enjoyable presentation. Thank you.
Thanks for your questions.
So David Gross has a question. It's a little bit long, so I'll try and summarize as much as possible. It looks like a scale up of the rovers from decades ago, this particular rover. Would you say that the next innovations in the rover will be incremental, i.e. material design updates for better traction or weight removal? And if so, is this just getting close to, are we close to the best rover design for Mars? And or will other planets and terrain need completely different innovations, completely different rovers? Or does this question minimize the innovations to get to the same kinematics up to the new size?
Yeah, so let me try to answer that, and David can feel free to ask follow-ups if I don't quite hit it. I think we are not limited by the mechanics of the rover at this point so much as we are by like the processing capabilities of the computers that we can fly to Mars. So Mars is a really harsh environment from a radiation standpoint. So the computers we send are pretty slow, pretty power intensive. I mean, your iPhone can like wipe the floor with these computers. So we could put, if we had more capable computers, we could put a lot more autonomy on board to make the physical rover, which is pretty good for like Mars, much more capable. And there are initiatives to do that. So I think in the future, the innovations will be less in the physical form factor and more in the like software autonomy space for the vehicle. That said, so in 1997, that was the first rover we sent, Sojourner, and it was like the size of a microwave. Here we are in actually MSL, and in 2011 when it launched was the size of a car. And we're seeing maybe something similar. So the rover is taking along with it a little helicopter, and it's a small kind of drone scale like helicopter that will only do short hops around like 90 seconds at a time. But it's intended to be a technology demonstration that we can actually fly a heavier than air vehicle on another planet. And who knows, maybe that helicopter is like the Sojourner rover of 1997. And eventually we'll get much larger like flying vehicles on Mars that could traverse much larger distances. Another vehicle that NASA has funded is something called Dragonfly, and it's a octocopter that's pretty large, like similar scale as like a Mars rover, that's going to fly at Titan. And so you are definitely seeing new methods for exploration that are tailored to the environment. Titan has a much denser atmosphere, so flying a heavier vehicle is possible. I hope that answers your question. I could probably talk about it for longer, but I'll stop there.
Got it, thanks. The next question is about picking up samples for geological tests. How do you get the rover and or samples back? Could you just talk a little bit more about that?
Yeah, so the idea is that we would send another mission to get those samples. So we would launch and land something called a fetch rover. So again, it'll be a rover wheeled vehicle. It will land on a base station that has a small rocket on it. The fetch rover will go out and pick up the samples that were left by Perseverance, bring them back to the rocket, package them up. The rocket would be sent up into orbit around Mars, and there would be a spacecraft there, likely the spacecraft that deposited the fetch rover would be there to collect the samples in Mars orbit, and then the samples would be returned to Earth. So, and we have examples of at least the sample return part of it. So recently, the Japanese just a couple of days ago landed some comet samples from a probe they sent. We just collected samples from an asteroid called Bennu with a mission called OSIRIS-REx, and those samples are now on the way back to land on Earth in 2023. So that's the idea behind getting the samples back. We'd have to send another mission to retrieve them.
Next question. What is the greatest danger to the mission of all the scary moments? What moment, once you're past it, is kind of the biggest milestone?
I think once the wheels are on the surface of Mars and we've confirmed flyaway of the descent stage, that's going to be a huge milestone. Launch was kind of up there too. Launch is pretty nail biting, but the vehicle we flew on has a lot of the rocket we flew on has a lot of has a pretty proven track record. I think as we're landing, like when we deploy that parachute, that'll be a really critical milestone. Only about 40% of the missions to Mars that have tried landing have succeeded. So the odds aren't necessarily in our favor. JPL, of all the ones that have succeeded, JPL has been the one to do that. So we have experience, but still that parachute is nerve-wracking. And then getting the terrain relative navigation to put us down in a safe place is also a little bit perilous. But we've tested it all. We believe we have a system that works. It's just sort of a matter of making sure we don't have any unknowns.
That's great. Who gets to name the missions and the rovers?
Yeah, so there's actually a national contest to name the rover, and actually there was a contest to name the helicopter. So the rover was named Perseverance by a middle school student in Virginia, and he wrote an essay about it. And actually, I got to I was part of the group that I guess sorted through some of the finalists, and ultimately it was up to, I think, like the administrator or associate administrator or something. But yeah, so he chose the name Perseverance, and this was all pre-COVID, but it's actually turned out to be a pretty apt name because it's been a really trying year for sure, and COVID hit right in March when we were putting the finishing touches on the rover and sending it out to Florida to get it launched. And all of the operations so far, we've done some things at JPL, but we've really tried to limit our exposure. So we're doing a lot of things remotely, which has been pretty smooth, but also challenging. So Perseverance has been a really fitting name. The helicopter is named Ingenuity, and it was named by, I think, also a middle school student here in the US.
That's great. Can you talk a little bit more about what the rover does for itself versus what requires direct control? And then are these systems like what we would call like AI or artificial intelligence, or are they more kind of hard-coded decision trees? Just what does the rover do for itself, I guess?
Yeah, so the sort of most basic thing it can do for itself is we have this whole behavior called fault protection, where if certain parameters are out of limits that we've established, certain thresholds, temperatures, power, whatever, the rover will go into what we call safe mode, and it will shut off everything it doesn't need. It will put itself in a configuration where it can be reached easily from the ground, from Earth. We can communicate with it easily. It'll make sure that it stays warm, and it can be kind of safe and healthy indefinitely. And that's sort of like almost like a fight or flight type analogy in a human brain. It's like kind of the most basic level of performance, I guess, enough to stay alive. When we're in like nominal operations, we have sequences that we can run on the rover. So it's kind of a more deterministic set of activities that are just like spelled out in computer instruction that it chugs through. On top of that, we have more autonomy. We have we have some features that can do simple task planning, and it can basically you give it it's more of a goal-oriented framework where you tell it kind of what you want it to do, and it balances resources and constraints and decides. And then there's a whole bunch of autonomy on the driving side. So it can do autonomous mapping and autonomous like waypoint finding, where you tell it where you want it to go, and it will map out hazards and avoid those hazards. And if it gets to a situation it doesn't know what to do with, it'll phone home and ask for help. I wouldn't say any of that gets into like AI formally defined. It's other types of autonomy, but I think AI could be a useful future. We're still pretty limited in our computation, so I think that'll be the bottleneck going forward.
Got it. We have another question from David Gross. Speculative futures question. Earth politics is very messy. Can you share your thoughts about how we are treating distant lands, the Antarctic, our moon, Mars, as commons that can be shared and not destroyed? What kind of care is/can be given to mission planning at JPL while still furthering our spacefaring capabilities, while maybe getting rid of the worst parts of the human practices of colonization from the past?
So yeah, I guess I can talk about that a bit. It's a really good question. I haven't thought super deeply about this. Maybe I should, given what I do for a living. And I also should say that like anything I say is like my own opinion. I don't like speak for JPL or anything. So NASA has NASA is trying to restart a return of humans to the moon, eventually to Mars. They have this program called the Artemis program. Artemis was the twin sister of Apollo. The idea is that this is going to be the program that lands the first woman on the moon, in addition to the next man on the moon, American man on the moon. So as part of that, NASA has rolled out this thing they call the Artemis Accords, which attempts to sort of define a set of rules of the road for space usage. Definitely borrows from like maritime concepts of the commons, and it's intended to be a framework that countries can agree to sort of minimize resource conflicts in the future. I know that NASA takes planetary protection extremely seriously. The amount of effort and engineering that went into like sterilizing this rover, because it is going to be collecting samples and sending them back, was actually one of the biggest engineering challenges on the whole mission. Like even harder in some senses than that entry, descent, and landing video I showed you. So NASA, it definitely does think very hard about how to avoid contamination of other bodies in the solar system. Another example is the Cassini mission. So Cassini was this really groundbreaking orbiter that went to Saturn, and at the end of its mission, instead of just letting it sort of go off and orbit uncontrolled forever, they actually decided to intentionally crash it into Saturn. The reason they did that is because Saturn has these moons, Titan and especially Enceladus. Enceladus is this icy moon it's covered with ice. It has, we believe, a water ocean below, and we believe it is one of the most likely places to actually harbor life in the solar system. We know that there are geothermal vents under the Earth that can provide sources of energy for life deep in our own oceans. So anyway, NASA elected to intentionally crash Cassini into Saturn, it not being a very hospitable place, in order to not endanger Enceladus or Titan, which are potential places for life.
That's really interesting. A follow-up question, somewhat. Were there any ethical decisions that you needed to make in your process, or I guess that NASA has faced in this mission more broadly?
Any ethical decisions, you said?
Yeah, ethical.
I'm trying to think. I know that. So I wasn't privy to all the planetary protection discussions, but like we mentioned, Adam Stelzner, he was very, very involved in those discussions, even at the level like going to Washington D.C. and briefing NASA about them. So he might have wrestled with some of these questions about the ethics of spreading our human reach to other worlds, for better or worse. I will say that, I mean, the exposure to ethics I've had at JPL is that there's a very strict code of conduct that we inherit from Caltech. You know, JPL is a division of Caltech. We do work on behalf of NASA, but we're all Caltech employees. So we're bound by the Caltech code of ethics, and that involves, conflict of interest disclosures and also ethics training and things like that. So as a JPL employee, we're exposed to ethics training and concepts, but I can't think off the top of my head of an ethical dilemma I've had as an engineer on 2020 yet, fortunately.
Got it, thanks. 1 second. We have another question. Just people saying they love this. This has been really informative. As an aspiring space scientist, I've loved hearing you speak. I have one more question here. Do you have any particularly favorite just stories or maybe books or movies from the history of space exploration?
So one of my favorite movies is Apollo 13 for obvious reasons. I mean, I'm a big Tom Hanks fan. It's a really compelling story. Let's see. I really enjoyed there was recently, we just had the 50th anniversary of the Apollo moon landing, and there was a documentary that was released in commemoration of that, and it was really great because there was not a narrator. It was just effectively the story was told through clips of people, who went through it, and it walked all the way through, basically walked through the whole mission, from launch day till the return, in the words of those people who experienced it. So I thought that was a really good documentary. If I think of anything else, I'll let you know.
Cool. One more question: what do private companies like SpaceX play any role in a mission like this?
Yeah, so there are a lot of private companies that provide components to missions like ours. We sort of assemble the rover at JPL, but we purchase a lot of the pieces from other companies. There's a company called, I think, Honeybee Robotics in Pasadena that supplies a lot of components to missions like ours. So yeah, but there is this big, emerging commercial space field, right? Like SpaceX, other launch vehicle providers like Rocket Lab. By virtue of what JPL does, it tends to be more a user of those services. So NASA has begun using SpaceX's rocket launch services. They launched the test mission on a SpaceX launch vehicle. Sentinel-6 was a NASA mission that just got launched on a SpaceX vehicle. Obviously, SpaceX is doing a lot with crewed missions to the International Space Station. So I think that as more commercial companies enter the space, JPL, NASA has become, it seems, more comfortable with the idea of having more public-private partnerships, and I think you'll just see more of that in the future.
Yeah, that's great. And you mentioned the International Space Station. Obviously, that's an international effort. Are any other countries involved in collaborating with this on this mission specifically?
Yeah, definitely. So, the entire instruments are provided from other countries. So, MEDA, the weather station that we have on the rover, that's a contribution from Spain. RIMFAX, which is the ground penetrating radar, that's from Norway. Let's see. The high gain antenna, which is one of the antennas on the spacecraft, also comes from Spain. There's a retroreflector from Italy. I'm sure I'm forgetting something, but there are a lot of international contributions to the project. And then we also have, our science team does have international participation as well.
That's great. Well, I think that's all the questions we have. So I just want to say thanks again for taking the time to speak with everyone. I know everyone really enjoyed it, and you can see from all the lovely comments in chat and in the Q&A that everyone really enjoyed it. So thanks so much for taking the time to present all this. This was amazing.
Yeah, no, my pleasure. It was really, really great to be able to share this with everyone, and it's a great project, and I'm just very grateful to be able to be a part of it and share it with you guys. So thanks for letting me come in and talk to you about it.
Thanks a lot. Have a great day.